Comes on. Great. I accidentally deleted 2 pages. Add them later. ठीक है. Just give me a minute. Yeah. So let's go ahead. So we got a square plate. Sigma is your charge density. Side is A. So exactly from the center, you kept a charge plus Q at a distance of A by 2. Find the force between them. Find the force between the plate and the charge. Yeah, homework problem, we'll see. How do we do this? Others, do keep your cams on. Okay. See, I'll tell you. First of all, it doesn't matter. You take any random shape. Basically, we have to manipulate the flux equation here. And let's say we have a charge Q. So due to this charge here, if you take a small point here, let's call small dA. At this point, the field is E. And this angle is theta. Okay. So the force on that small sheet will be E into dq, which is E sigma dA. Okay. From here, if you look at the forces, so if you take the F components, F cos theta components, net force downward will be integral F cos theta, which is integral E sigma dA. So this gives you the force between the charge and the sheet in the vertical direction. Horizontal components, we have no idea. Horizontal components will be E dA sine theta, that we won't be able to calculate it. We'll see. So E sigma dA cos theta. So if sigma comes out, you end up with E dA cos theta, which is sigma integral E dot dA, which is nothing but sigma into flux through the sheet due to the point charge. This gives you force in the vertical direction. This does not give the net force. So you can find the force between the charge and any random sheet if you can somehow calculate the flux, and only in the vertical direction. If there's a symmetry, sine theta component cancels out, like the previous question. Now, in our case, when you look at the square plate here, the information is given exactly, proper to figure it out. So if you construct a cube of side A and you kept the point charge exactly at A by 2, meaning it became the center. And last class we proved the flux through any closed surface is q by epsilon. Since there are 6 faces, the flux through each face will be q by 6 epsilon. And here there's a symmetry, so there is no horizontal component. Getting it? So the force on the plate will be sigma into flux, which is sigma into q by 6 epsilon. Is this making sense? So since there's a symmetry here, there will be no horizontal component. But if you take any random shape, first of all, calculating flux would be a problem. But because it is a cube, it is easy to figure it out. So basically, we can use that logic and finish it off. So here, if there is an E, the horizontal components cancel out. It's a pretty good result. You can remember this. Sigma into, so basically we manipulated the flux equation to give us force. Any doubts on this? So the horizontal component that turns out to be sigma F sine theta, which is integral E sigma dA sine theta. We cannot calculate this. So E dA sine theta is nothing. Clear? Now, in the last class, that last question. Now, this thing now, the dipole, there is a better version of this. So if you have a dipole P1, this would solve this next problem also together. And if you have another dipole P2, but this time both the dipoles are at an angle theta. And the distances are. So the idea here is, at this point, the field so P1, at this point, the field will be 2kP1 by r cube. It's on the axial line. So potential energy of the system, U is equal to minus P2 dot E1 bar. This turns out to be 2kP1 P2 cos theta by r cube. That's your potential energy. And what is force? Force is minus du by dr. So if you differentiate this, you end up with cos theta is constant minus 1 by r cube, minus 6k p1 p2 by r cube into cos theta. This is a more superior form of writing, because previously we derived only for axial line and perpendicular. This would give you both at the same time, and it gives you even much faster. So this is a much better form. It gives you even in terms of angles. Last time what we did was only giving axial length. So based on this, we can do this also now. It is the exact same question now. So here we'll find the field due to the ring, which is kq r root 3 by, take it as x actually, we'll do it as a variable and then we'll substitute kqx r square x square whole power 3 by 2. So potential energy will be minus p e cos theta kqpx cos theta by r square plus x square whole power 3 by 2. This is the potential energy. Force is minus du by dx. Differentiate it, you'll get the answer. Clear? Since the dipole is very small, we can do this. The dipole is so small, we can assume the field is almost uniform at that point. So you'll get the force as a function of distance x. Clear? So find the potential energy and you'd finish it off. If you want to find torque, torque is actually easy. Torque is simply P cross E. So the main idea here is, since dipole is very small, we can assume the field is almost uniform there. Clear? So you could use the same technique on dipoles also. So it doesn't matter any system you bring. If the dipole is very small, find the potential energy and differentiate it. Yeah. If you did this, you're right, Arya. All clear with this? The Gauss law thing is clear. Sigma into flux.
Sir, can you show that page where we did this question? The square plate one?
Okay. These pages now I accidentally deleted. Hmm. Clear? Next one. So we got a cube here. Let's call this 1, 2, 3, 4, 5, and the side is 6. And we have a charge q here. Find flux through the cube and find flux through each face.
So sideline.
It doesn't matter, right?
पक्का.
Calculate करके देखो. Tell me if you are getting it.
ठीक है.
But since you're asking, I'll give it to you. Since I'm a good person for today. Okay, get for the each face. That's what is more interesting.
अच्छा सॉरी नहीं चाहिए साइड.
Okay, first one is the easy one. So in this big cube, if you take this small cube here, so this point charge is q. Agreed? The flux through the big cube is q by epsilon. Now there are since 8 small cubes. The flux through each cube, they divide equally because of symmetry, is 1/8 of q by epsilon. So that's the flux. Okay. Now we want to find the flux through the faces. Now see, now there is something here. When you look at so when the point charge is here, try to see clearly here. How will the field lines go? The field lines through the surface are going like this. And for this thing, the area vector is like this. Can you see how it is? So whichever face is touching the charge, the field lines will pass through the plane, isn't it? You're supposed to take the field on the plate into area vector to get the flux. But any face that touches the charge, faces touching the charge, have field lines parallel to the surface. That is, E is perpendicular to area. Meaning, if you look at this field lines here, look at for this part, the field lines will be like this. Are you getting? So whichever side you're touching, the field lines will be parallel to that surface. So if you name them 1, 2, 3, 4, 5, and 6. So flux through 3, 2, and 6 is 0. So the charge is touching three faces. So the field is perpendicular to area, that is 0. And the remaining 3 guys, 1, 4, and 5 are equisymmetrical. So whatever the flux is getting, it should divide among these 3 surfaces equally. So this will be 1/3 of the flux through the cube, which is q by 24 epsilon. I hope you're getting this. All the faces won't get equal flux. The 2, 3, and 6, which are touching the charges, the field lines are perpendicular parallel. So the field becomes perpendicular to the area vector. So the flux is 0 through them. The total flux through the cube is q by 8 epsilon. So the remaining 3 faces will take 1/3 of that q by 8 epsilon. Clear? This is the standard one. So let's change this a bit. Any doubts on this? All clear, right? Now, so this charge which you kept here, plus q, case 1, so this is your center. This is case 1. Case 2, case 3. This is 1, 2, 3, 4, 5, and 6. Now, look at this thing. Case 1, the charge is slightly moved away. Charge is slightly moved. Case 1, away from center along the diagonal. Means you took it just out of the cube. So that point charge is on the corner. You just pulled it slightly outside along the diagonal symmetrically. Case 2, towards the center along the diagonal, body diagonal basically. Case 3, again it moved slightly towards center, face center of phase 2. You getting what we did? So the charge Q is on the corner. Initially, case 1, you just slightly pulled it outside, very little. Case 2, you slightly pushed it inside. Case 3, you pushed it slightly along the diagonal, meaning on that face. Find the flux through each face. How do we do this? Think. Take a minute. Then I'll show you one. No, Adrit, that is not the answer. Okay, so first I'll help you with case one. Listen. For case one, since it is pulled out, so the charge is not on the cube, okay? Since it is pulled out, the flux through the cube becomes zero. Are you getting it? But since distance is very small, it is slightly displaced. You really didn't change the field or the angles at any point. Since it is slightly displaced, the flux on, so the three things which we calculated, 1, 4, 5, flux on 1, flux on 4, and flux on 5 will still remain q by 24 epsilon. Isn't it? Think about it. If you just look at this face, this charge which was here, it went slightly here. This plate won't even realize that the field changed, isn't it? E is same, angle is same, everything is same. So 145 will say, okay, we don't know what happened exactly. Nothing happened. So they will give the same flux. But for the other three now, this guy has come outside, right? Now the lines are not parallel, they're actually crossing. And it is symmetrical. We can clearly see. So the flux through the other three faces, flux 2. So total flux, flux 1, flux 4, and flux 5. Plus the other three things now, flux 2, 3, and 6. The total should be 0. And if you see by symmetry, all are equal. These are identical due to symmetry. That is the reason you have to pull it along the body diagonal. If you pull it in any direction, the symmetry will go off. So these are similar. So that will be 3 times flux due to 2 should be equal to 0. So minus q by 8 epsilon. So this guy would be minus q by 24 epsilon. Make sense? So the other three will contribute equal amount in flux in the opposite direction. The total flux is 0. Is the logic making sense? So the biggest idea in the question is, since you moved it such a small distance, 1, 4, 5 will not even realize that something changed. Their flux will remain constant no matter what you do. Now can you do case 2? Using this idea, can you do case 2 and case 3? Case 2, you pushed it inside. Case 3, you pushed it along the face diagonal. And if the angle has changed by very little, won't the flux through the magnitude also will go to infinity, na? Kq by r square. Angle has changed, but E also has become very big value, isn't it? Now, what about the second case? See, in case 2, Again, the idea would be same. The flux due to 1, the 4, and the 6, 5. These guys are unaffected. But now, since charge is inside, the charge has gone completely into the cube. Therefore, the total flux through the cube is q by epsilon. Therefore, the flux due to the remaining 3 guys should be 1/3 of the remaining flux. How much is that? So q by epsilon, that is q by 8, so 1/3 of 7 q by 8 epsilon. Make sense? Because these three together are giving how much? Q by 8 epsilon. So flux 2 plus flux 3 plus flux 6 by symmetry plus flux 1, 4, and 5 is q by epsilon. This will give q by 8 epsilon. So automatically this should give 7 q by 8 epsilon, and each will take 1/3. Clear? The total should be q by epsilon, no? What about the third one now? What if you push it along the phase center? Yeah, I think so, Ishan. That looks right. Let's see. Try, I'll give you a minute. What if you push it along the phase center?
So, but then how does that make sense? Like, if you push it out, you're getting zero flux through the 2, 3, 6
Total cube.
No, yeah. But like when you push it in, you're suddenly getting more flux than the other 3 sides.
Because the flux is charges inside the cube now.
Still, but
When
like,
you are exactly on the surface, you have something. When you're inside, lines are actually crossing out, right? If you put a charge here, every line crosses will cross it out again. But if you're inside, only lines are going out. There's nothing coming inside. It's about the number of lines, isn't it? It's only getting messed up with that 2, 3, 6 only. 1, 4, 5 are unaffected. Look at case 3. Case 3 is interesting. Whole game changes actually. Again, as usual, the story, the 1, 4, and the 5 will remain same. So this is the main thing you need to understand. These things guys won't get affected. But now the problem with the cube is when you push the charge this side plus q, I'll construct one more cube like this. So the flux through each cube will be q by 2 epsilon. Agreed? Each cube is contributing half of flux. Now in that, one, 2, 3, 4, 5, and 6. The charge q is on the surface 2. Just now we saw if the charge is lying on a particular phase, that flux will be 0. Flux 2 will be 0. You're getting it? Since the field lines will be parallel. So flux 1, flux 4, flux 5, plus flux 2, plus the other 2 guys who are left out. Who is that? Flux 6 and flux 3. So this total flux should be q by 2 epsilon. These guys are q by 8 epsilon. This guy is 0. So flux 6 and that thing both will be equal. 2 times flux will be q by 2 epsilon minus q by 8 epsilon. That would be 3q by 16 epsilon. Why I won't get 145? Because you're displacing by small amount. So you mean to say if I keep a plate here and there's a charge q here, from here, if I move it just beside it here, will the field at every point change? Will the angle change? So you can neglect that, right? But the problem, you can't do that for this sheet because it is touching here. Once you took it out, it is not on the sheet anymore. The field lines won't be parallel. So those fluxes will change, but the things which are pretty far won't change. You're getting it? Basically 145 are pretty far from the charge and your displacement is so small, it doesn't affect them. Is case 3 clear, everyone? Arjun, got the idea here?
Yes, sir.
Anyone not clear with this? Please ask me. Next one. So you can play with the cube like this. Next one. We have a it's not bad at drawing it. Okay. So we have a so this entire base is a charged sheet. So the top part is completely a cylinder. You're getting, so this entire, the cylinder has a charge plus Q. This sheet ka charge density is sigma. L is the length, 2r is the diameter. And this length is much greater than r. It's a pretty long cylinder. So this is a, if you look at the side view, it looks like this. So on the cylinder, the charge is like this. And this sheet niche is sigma. So this bottom part is closed by a rectangular plate. Find the force between them. So the up one is plus Q, niche is plus sigma, so they will repel. So what is the force between them? It's a half hollow cylinder. Since the length is very big, you can neglect the edge guy effects. I hope the question is clear. First thing, see. Now, because it's a cylinder, we know the field will be radial. So if you take any point charge here, dq, you can clearly see this makes an angle 90 degrees, isn't it? So that means whatever field length you get, 1/4 of the field length will pass through the base. You getting it? So every point on this thing, so every dq charge contributes 1/4 of the flux. Which passes through, let's call this line AB. Because see, if you look at the dq charge, the field lengths will be going in all directions, but you're taking 90 degrees here, so 1/4 of that will cross through. So if you take a plus q here, so here 360 degrees is giving q by epsilon. So 90 degrees will give 1/4. This works only for the cylinder. Huh? This works here. Normally you should take actually 360 degrees into like a solid angle. Valid here, since for a cylinder the field is radial. It's a long cylinder. How will the field be for a long cylinder? Remember, we draw the diagram, the field will be like this. The lines are just coming in the same plane. So what is the flux between them then? The flux passing through the base will be q by 4 epsilon. What is the force between them? Charge q sigma into flux. हो गया ना, sigma q by 4 epsilon.
So how is it q by 4 epsilon naught?
What were you listening? What I said this?
I got that, लेकिन total कैसे हम बोलेंगे q by epsilon naught है? So what if some charge is outside the half cylinder?
Some charge is outside the half cylinder. What are you talking?
I didn't get how you will say q by 4 epsilon naught
Okay. This dq belongs to whom?
for the cylinder.
Okay. So that is contributing how much flux?
Okay, समझा.
So that dq is actually belongs to whom? That plus q only, na? You're dividing this plus q all into small pieces, isn't it? dq, 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 dq. And we proved every dq on this hollow cylinder will give only 1/4 of its contribution.
Yes,
The total charge q on that will give 1/4 of the contribution. Is that logic clear, everyone? Next one. Clear, na, Udian? Maulika? Rehan.
We can take elements and find the value of sigma, right?
Q, which sigma? Sigma is given, na, actually for the bottom sheet. What you want to find?
Yeah, sorry.
Yeah. Next one. So we have a ring here, charge plus Q. And we have a disk here, which is sigma. And it is given the field line from the edge. They go like this. So it is given. And this field line makes an angle of 45 degrees. So at this instant now, this is making 45 degrees when it is about to leave. Find the force between them. Find force between the charged ring and the disk. Sigma Q by, yeah. The previous one, this thing has a relation, same thing. If you just look at the ring here, think about it. If you take the ring exactly at the center, what is the field at the center? It's a null point, right? That means all the field lines which are coming here, so this first line is going like this, meaning then the another line would go like this, the another line would go like this. Eventually, right, if you see at the center actual line, this line should become like this, isn't it? Meaning all lines will start converging something like this. If you look at the actual line here, so this line will be like this line will be like this. So as you get closer and closer, finally this line will become parallel, isn't it? Getting it? So that means for this guy, that 45 degrees, all these lines are passing through the disk. So can I say the line from this line to this line, all these lines will pass through the disk? Is that making sense? So this is making 45, and with the vertical, that is another 45. So if you just look at the point charge here, dq, so this is that 45 degree line. So this is another 45 degree. That means all the lines starting from here and this line will pass through the disk. I agree, it is giving out lines in all directions. So flux through the disk will be how much? 45 degree by 360 into q by dq by 8 epsilon. So that is 1 by 8 epsilon. Therefore, force would be sigma into flux. Once you got flux, game is over. Check. What is the field along the actual line, Ray? Saina? For a ring, what is the field along the axial line? So at this point, how is the field? This way, right? Means what? All these lines are becoming like this, isn't it? All clear with this? Field along axial line is along it. Clear? Next one. We have a cube. 1, 2, 3, 4, 5, and 6. This time, it's not a point charge, but you have a line charge. This is plus lambda 1, infinite line charge. It is passing through one of the side. And this is another line charge, which is plus lambda 2, another infinite line charge. Find the flux through each face. Instead of point charges, now we have line charges.
For this also, we don't require the sideline.
Take it and prove it. Flux scale, what matters? Only the number of lines, isn't it? If you take a big cube or a small cube, why will the lines change?
No, because. Achha, wait, let me try.
Infinite line charge है ना रे, फर्क नहीं पड़ेगा. Can you find the flux in the cube only due to the line charge? Forget about the face first. Find the flux inside the cube due to the line charge. Okay, sinus is 1542. Due to one line charge, na? Right, Saina? Due to both. There are two lines here, don't forget.
Yeah, due to both.
Due to both, क्या? ठीक है, देखते हैं. Now, first, let's see how to find the flux due to one line charge. So it's like we are taking 4 cubes, isn't it? And now your line charge is passing through the center of them, isn't it? Is this making sense? That line charge, so if you keep 4 cubes, it is passing through them. So this is the charge inside, so which is lambda into L. So lambda into L is the charge inside. I think you need side right here.
Yeah, because.
You're right.
Right.
Charge nahi aa raha hai. Side is take it as L. So lambda into L. So then flux through each cube will be how much? 1/4 of lambda L by epsilon. Agreed? So if you have an infinite line charge passing through one corner, one side, the flux passing through the cube is lambda L by 4 epsilon. And now again the same story. Whichever face is touching the line, those things will have zero flux. because the field becomes parallel. That you can see more clearly here. So if you see for this guy, plus lambda 1, you can clearly see these lines are going like this because the field is radial. So flux through the faces touching the line charge is 0. So 1, 2, 3, 4, 5, 6. So due to this red one, I'll call it phi 1. Due to the lambda 1, who all are 0? 1 is touching, 3 is touching, 5 is touching, 4 is also touching. The only two people remaining are 2 and 6, which will take equally by symmetry. So they will take half of the total flux, which is lambda L by lambda 1 L by 4 epsilon. Clear? Same logic I can use for this guy now, the green line. Lambda 2. For lambda 2, who is touching? 2 is touching, 6 is touching, 4, and that 5 is also touching. Who is not touching? 1 and 3. So they will take equal flux. So 1 by 2 lambda 2 L by 4 epsilon. I think there is no common, no? So 1, 3, 2, 6 will have flux. Yeah, and that 5 and 6 will always have, 5 and 4 will always have 0. Easy? Next one. There you can keep on playing with more varieties of questions flux, but these are main ideas there. Turn in the page. The electric field in the region is given by xi cap plus 2y j cap plus 3z k cap. Find flux in a small cuboid. Of sides dx, dy, dz. And find the charge enclosed by a sphere. Now this field is not uniform, meaning the entire region must be filled with some charges. So in this field, if you take a sphere at the center, so the field lines are going in all random direction, how much charge is inside that sphere? God, flux is scalar, right? How are you getting I cap, j cap, k cap?
The cuboid has a corner on the origin.
No, it's a small cuboid dx dy dz. It doesn't matter. X square by 2, y square by 2, 3z square by 2. Nah, you guys are goofing up. See, so at some random place, if you take a small cuboid, let's say this is dx, this is dz, and this is dy. Now, just try to understand on this face, let this field be Ex. On this face, let the field be Ex plus Dex. Agreed? So for that small change in dx, the field has changed by Dex. So flux on these faces, getting it only the x ka faces we are talking about, flux would be Ex plus Dex into what will you take area as? Area is dy into dz, na? So you take the horizontal field, but the area will be dy and dz minus Ex into dy and dz. So this will be Dex into dy and dz. This is a flux only due to the horizontal field, due to Ex. Make sense? Similarly, I can use the same logic and say the flux due to Ey field will be Dey. Now the area will be dx and dz. Similarly, flux due to the Ez field will be Dez, dx and dy. I hope this is making sense. So let the field on one face be Ex. If you go little distance dx, the field will change by small Dex. So what you're end of the day finding is flux through the closed surface, right? I'm not trying to find the flux on each surface. So the total flux through this cuboid, flux is a scalar quantity, I can directly add it up. And here Dex is given, what is E bar? Xi cap plus 2y j cap plus 3z k cap. So this is your Ex, this is your Ey, and this is your Ez. So differentiate, Dex will be dx, and that guy would be dy dz. Dey will be 2 dy, that guy would be dx dz. And this guy would be 3 dz, that guy would be dx dy. If you add all of them, you end up with 6 times dx, dy, dz. That is a flux through a small cuboid, which can be written as 6 into dv, where dv is the volume of the small cuboid. And for the b part, you want flux through the sphere. You just have to integrate all the cubes. So you end up with 6 into what is integral of dv? That is the volume of the sphere. Which is 6 into 4 by 3 pi r cube. But we know flux is nothing but q by epsilon. So from there we get q charge enclosed is equal to how much? 8 epsilon r cube pi. That's the charge enclosed.
Here आपने क्या किया?
This is the small cube, right? So if you add all the cubes, what will you get? Within a sphere. Volume of a sphere.
Okay.
What is the integral dv? Volume, right? So if you want flux on a sphere, then you have to integrate the volume on a sphere. Isn't it? If you take a sphere and उसमें छोटा 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 cubes लेके सब add किया, तो sphere का volume आएगा. Please have a look at this. So the main idea is this. You should not take full field on every face, isn't it? On dy, dz, only Ex will act, remaining as 0. Any doubts on this? All clear? Neil, Saina, clear with this? Push, got this thing?
Yes, sir.
Ali, Aditya, Yasha, Molika, clear na? Rehan, Arjun,
Yes, sir.
great. Going ahead.
Just 1 second.
Yeah. No. Gaussian surface. So what's a Gaussian surface? So basically it is any closed surface, an imaginary closed surface where flux is calculated. So if you see, right, till now we played around with actually Coulomb's law se sab prove karke we used it. Now we are actually defining the Gauss law. Imaginary closed surface about which we went in the wrong order actually. But meaning, if you see in the time order, right, first came Gauss law, then came Coulomb's law. But we used Coulomb's law and we proved Gauss law. It works out. About which flux is calculated. Again, remember, it is an imaginary surface. It doesn't exist. It is just your imagination. So what Gauss law says is, maybe not write all big terms. What it simply says, the flux enclosed E dot dA is the charge enclosed by the figure by epsilon. This is what we are playing around till now. The meaning of this symbol now is called closed integral. The moment you put that circle, it is understood you are integrating over a closed surface. If you just put normal integral, you're integrating over a surface or something. But a closed integral implies that surface which you're integrating is closed surface. They're mathematical representation. So, example, if you take some random surface here, this is Q1, this is minus Q2, this is Q3, and this is Q4. So here, the flux, when you write integral E bar dot dA, now listen carefully here, there's a theoretical thing. When we say Q enclosed, so exam will ask you like this. In the Gauss law, E dot dA, E is due to which charges? This E bar, which we are taking, is the field due to all charges. So Q1, Q2, Q3, Q4, all charges. Whereas Q enclosed is only the enclosed charges, which is Q1 minus Q2 in this case. That is because when Gauss was doing this experiment, think about it. How will you differentiate who is giving how much field? You can always calculate net field, but the end result comes out as if only the field is due to the inside charges. And what is the reason? We'll see it in the next page. That we actually proved. Remember, any charge that is outside will contribute zero flux. So
Yes,
it
sir.
really won't matter by adding it. You are just adding zeros on the left hand side. So it really won't matter. This is your Gauss law. Gauss law is useful. It makes your life simple for certain cases, right? It is useful to find field. Turn in the page. So if I expand this integral E dot dA, this is nothing but integral E1 bar dot dA plus integral E2 bar dot dA plus integral E3 bar dot dA. So you're basically taking the field due to everyone. E4 dot dA. This is Q1 minus Q2 by epsilon. But we know these two will be zero. Charges outside do not contribute any flux. That's what is happening. Basically, just added zeros on the left. So be careful. Exam they'll ask you like this. They will say E1 plus E2 dot dA is Q by epsilon. It is right. integral E1 plus E2 plus E3 plus for dA is equal to Q epsilon. That is also right. You're getting it? If you take only Q1, Q2, your answer would have been still right. You basically just added zeros there. So this is the reason why the flux is only coming due to the enclosed charges, because E3 and E4 are creating zero flux on the surface. So this E can be E1 plus E2 plus E3 plus E4, or you could have taken E only due to E1, E2, it would have still worked out. Clear? So what is this Gauss law useful for? Gauss law is useful for finding field due to symmetrical charge distributions. So if there's a charge distribution which is symmetrical, it's quite convenient to use Gauss law. So Gauss law is valid for any charge distribution, but it is only useful if there is a symmetry. So let's see a shape. All clear with this? Now let me take an example. This shape we didn't do in electrostatics, huh? Infinite, hollow, charged cylinder. So you have taken an infinitely long cylinder whose radius is r. It has a charge on the surface. Let's call it sigma. So I want to find the field inside and outside. So this is what we do. Consider a cylindrical Gaussian surface so for r less than r, so we take a Gaussian surface like this, whose radius is smaller, length is L, completely closed. We can see by symmetry, if the field exists, it should be radial. By symmetry, so that is the important thing. If you don't have symmetry, you can't say field is radial. Meaning field is going away from the center, if at all it exists. So meaning you are assuming the field is like this, the field is like this, and on this thing the field is like this, on this field is like this. And you can clearly see here for these guys, the area vector is like this. So the top two disks will have zero flux. This is area and this is area. So flux will be the field E into 2 pi small r into L. That is flux. That should be equal to Q enclosed by epsilon. But since it's a hollow cylinder, charge enclosed is zero. Therefore, E is equal to zero. So there is no field inside a hollow cylinder. If we take r greater than r, that is the outside point, we are considering, let's say, one more Gaussian surface like this. Now the flux will be E into 2 pi RL, same thing. But now the charge enclosed, now there's a charge inside, which would be sigma into the surface area of that hollow cylinder, 2 pi r into L by epsilon. So 2 pi L will cancel. You end up with E is equal to sigma r by epsilon small r. Is this clear, everyone? How we got the field? So we are assuming the field is like this. So if you try to plot the graph for E versus R, this actually kind of looks like hollow cylinder, hollow shell ka field. It will be 0, then suddenly it goes up and then decreases. But remember, it is proportional to 1 by r. For a point charge, it was 1 by r square. Is this clear? How did we use Gauss law to get the field? So these shapes, we didn't have it in electrostatics. So consider a Gaussian surface within inside of radius small r. You can actually see it is a hollow cylinder. The field will be 0, but still be provided. But if you take it outside, now there's a charge enclosed because all this charge will be inside now. Clear, everyone? So this is how Gauss law is useful to find field. Other than this, there is no big practical applications for Gauss law as such. This one and the force calculation. Force is sigma into flux. They are the main things.
When the R greater than the capital R case, through the top surfaces, can we find the flux?
That will be 0, no? Because field is radial. So area vector will be perpendicular, isn't it?
Whichever that also we assuming. Okay.
No, see, that is the whole point of infinity, right?
Oh, okay.
Because I'll tell you, infinity has a very special property. By infinity, every point is a midpoint.
Right, yeah.
And if it's a midpoint, by symmetry, the field has to be radial. You can't have a vertical component.
Right, got it.
That's why you can have an infinity. If you take a finite thing, this concept won't work. It will be a blunder. इसीलिए ना finite rod का remember you used to get 2 components.
Yeah.
We can't do that. Clear? Take a break. Come back with 7-2. Any doubts so far? Ask. Come back in 10 minutes. Chalo. Now, I showed you for infinite hollow charge cylinder. You guys try for a infinite solid cylinder. Radius is R. It's uniformly distributed everywhere. Rho is the volume charge density. Find the field inside and outside. Especially they'll ask you plot E versus R graph. That would be more better. Find E bar as function of R. R is distance from the radial line. Same thing. I showed you for a hollow cylinder. Same logic used for solid cylinder. Let's get this. Others, do keep your cams on. सिग्मा नहीं है राजन, यहाँ पे रो है. See. So for R less than equal to R, not to be a continuous function. So basically inside. Again, since it is a symmetrical shape, we can assume the field will be radial. So we are taking a Gaussian surface like this. E is radial. So that flat surfaces won't have any flux. There'll be a perpendicular area. So flux would be E into 2 pi small r into L. where L is the length of that cylinder. This should be equal to charge enclosed by epsilon. Charge enclosed is rho into that volume pi r square into L by epsilon. So E turns out to be rho r by 2 epsilon. It's a linear function. Yeah, I think most of you did get. Now, if you take r greater than equal to r, that is the outside points. Same logic, we will use a bigger Gaussian surface. This time r is outside. The flux will still be same, E into 2 pi small rl. But this time the charge enclosed would be rho. Now see, the charge will stop at capital R. So rho into pi r square L by epsilon. So this would be rho r square by 2 epsilon small r. So if you try to plot a graph, if you see the field actually looks like a solid sphere. It increases linearly and then decays. Clear? This is the field due to an infinite solid charge cylinder. Now cylinders we didn't do in electrostatics. You couldn't integrate. These are quite complex to integrate. But Gauss law gives you the answer. If you give me a finite cylinder, but we are gone. We can't do a finite cylinder. Gauss law won't be applicable. All clear with this? Next one. Next one. So you have a uniformly charged sphere, not a uniformly charged sphere. Charged sphere whose density rho is equal to rho naught r power n, where r ka value lies between 0 to r. Meaning the more you go away from center, you have more charge. It is applicable, Rasaina, but you can't use it. That E won't come out of the integral, na? Field won't be radial. You won't be able to calculate flux. If you take a finite thing, there is no guarantee field will be like this. Field can be like this also. It will be at an angle. Then the flux will be E into A into cos theta. And I can't find that theta. Now look at this charge distribution here. When R is 0, the field is 0. Go out, little increase, then more, and then more. So as you go outside, the field is becoming more and more. The radius is R. Find the electric field as function of R. R is distance from center. This is for n not equal to -3. Yeah? You will see why. But if this question comes right, generally I've seen a standard question would be like this. If rho is equal to rho naught r power n, then the field E will be proportional to r power n plus 1. You can remember that thing. Whatever the charge density, field will be n plus 1. That would be a straightforward question. Let's try to prove it now. For example, see, if rho is constant, uniformly charged sphere, then n is 0, right? Then this would be r power 1, a linear function. So if it was some kind of integer question or something straightforward, you could figure it out. Rho r power n plus 1 by 3 e. Okay. Try. Others, I'll give you a minute. So first let's take a Gaussian surface inside. Right now, but before that, there is a, let's find the charge before only. So if you take this small sphere of radius r, inside this sphere, let's take a thin shell of x radius and dx thickness. So the dq charge on the shell will be rho naught into r power n 4 pi x square dx. Now understand, n is constant here, x is a variable. So charge on that sphere, so q is the charge on a sphere up to radius r, will be rho naught 4 pi integral r power n integral x square. This is also have to include actually rho naught x power n into 4 pi x square dx. So that would be rho naught 4 pi x power n plus 2 dx. This will go from 0 to r. So this is rho naught 4 pi by n plus 3 into r power n plus 3. So this much charge you have if you take a sphere of radius smaller. Clear? Now, for r less than capital R, the flux will be straightforward, E into the surface area 4 pi r square. That should be the charge enclosed by epsilon. Now try to understand, this is the charge from 0 to smaller, which we have calculated already. So E into 4 pi r square, rho naught 4 pi r power n plus 3 by n plus 3. This is the reason why I didn't take n is equal to minus 3. Then you'll get a ln ka term there. So you can't use x power n formula for n minus 3 here. 4 pi will cancel. We get E is equal to rho naught r power n plus 1 by n plus 3 and epsilon. For r greater than r, the charge is constant. Even though the charge is variable, the total charge of the sphere is constant. E into 4 pi r square. This would be the total charge, which is rho naught 4 pi r power n plus 3 by n plus 3 epsilon. Field will be rho naught r power n plus 3 by n plus 3 epsilon small r square. Check. There is still a symmetry here. Radially, there is a symmetry. At a given x, the charge distribution is same. Have a look at this. So if someone gives you a non-uniformly charged sphere, which is still radially symmetry, you can still find field using this. So this is what I was saying. Gauss law is quite useful when there's a symmetrical charge distribution. You give me some non-symmetrical charge distribution, it is of no use. You can't do anything with Gauss law. Clear with this? Everyone? Any step you're not clear? Next thing. Can I go ahead? Maulika, Swastika, clear? Utsa, Vartika, Palaksh, Neil. Great. Next thing. Infinite charge sheet. Do you guys remember the formula we derived it? We took that disk and we made disk R infinity. You need to mug up all these results. The infinite charge sheet So sigma is there. So this is what we do. Consider a Gaussian surface. Passing like this. So basically this is the charge enclosed inside. The field is E, area vector is A, the field is radially away from here by symmetry, this is A. So the flux will be E into A plus E into A. That should be equal to Q by epsilon. So 2 times EA, the charge enclosed will be sigma into that area A by epsilon. E is equal to sigma by 2 epsilon. That means if you take an infinite sheet, or if you take a negative sheet, the field lines will be radially away, constant magnitude, no matter how far you go. For a negative charge, they'll be inside. Now, if you take an infinite plate, the difference between a plate and a sheet will have two surfaces. See, in a sheet, now, when you look from left side or right side looking at the same molecule, are you getting it? The sheet is so thin, it's one molecule thickness. When you see from right or left, there is only one molecule. But in an infinite sheet, there are two surfaces. Infinite plate. So an infinite plate is like two surfaces. So each surface will contribute sigma by 2 epsilon. So the field will be sigma by epsilon and sigma by epsilon. Results are more important, you can remember this. But derivation is like this. You consider a Gaussian surface which is passing through the sheet. So this, the thing which is shaded here, this would be the charge enclosed. You could have taken a cube also, it would have worked. So this is one more result you need to remember. Nee. See, problem kya hai na? For example, in this thing, if you take a sphere like this, there is no restriction. But problem kya hoga? The field is like this, area is like this. You can't calculate flux, no? So choose a Gaussian surface such that there is some symmetry so that you can calculate the flux easily. The whole story is about calculating flux. Clear, everyone? Now, let's say there are two infinite planes. This is an xy plane, which has a charge plus sigma. This is your yz plane with a charge minus 2 sigma. So two infinite sheets are placed along xy and yz plane. Draw the equipotential surfaces. Draw equipotential surfaces. Let me make it a little simple for you. Draw the electric field lines and draw the equipotential surface. Draw the field line diagrams and draw the equipotential surfaces. You need the field line diagrams to draw equipotential. Try. I'll give 2 minutes. Options, they'll give 4 options. You have to choose the lines. The yz is negative charge. Huh? Let me mark it with a different color. So this is plus sigma. This guy is minus 2 sigma. You're getting how it is? Both the sheets are crisscrossing. Hmm. Kind of Aryan. That. Try, everyone. 2 minutes. It's a good one. Simple. It's a proper main cell question. ओके, हाइपरबोला नहीं है रे, स्ट्रेट लाइन आएगा गॉड. Try. I'll show you. You can try. You can verify. I'll give you a minute more. Yeah, right, Lakshika. P potential surfaces. See, first thing, this thing, the green one, the field will be away from the sheet. Sigma by 2 epsilon, sigma by 2 epsilon, sigma by 2 epsilon, sigma by 2 epsilon. The red one is negative, so it'll attract here. So 2 sigma by 2 epsilon, which becomes sigma by epsilon. Sigma by epsilon, sigma by epsilon, and sigma by epsilon. So this is the field everywhere. So if you look at the resultant here, the field lines are actually like this. So this is angle theta. The same thing here also. This is angle theta. So I'm choosing this as theta. So tan theta will be opposite side by adjacent side. So this is tan theta is off. So now if I try to draw them, this is minus 2 sigma and this is sigma. The lines will go from the positive charge. They'll end up there. You'll get lines like this, where this angle is theta, where tan theta is equal to 2. You're getting how it is?
Tan theta half or 2?
Half. I took tan theta with the x-axis. Now these are field lines. And remember what are equipotential surfaces? The equipotential surfaces are perpendicular to the field lines. Do you remember? Or you can say the other way, the field lines are perpendicular to the equipotential surfaces. Meaning you have to draw perpendicular lines to these surfaces. So that means we need to draw surfaces like this. You get something like this. Making sense? So this will be perpendicular to these surfaces. Yes, sir. Something like this. These are the equipotential surfaces. Clear, everyone? So generally, when they ask you equipotential, it is preferable you go from field lines, and from there, that would be an easy way. Draw the field lines and draw perpendicular planes to that, and you'll get it. Any doubts on this? Adrit? Clear, na? Anusha? Ishan? Clear? Ali? Palaksh? Yasha? Vidyut? Clear, na? Going ahead. Saina? Great. Next thing. Now, this would be the most important part of, the Gauss law, what we're doing now. The field inside a conductor and the charge distributions. So listen carefully. We'll be doing the theory part today. Next class, we'll do more problems on this. So field inside a conductor. So consider a conductor placed in an external electric field. Now see what happens. Now that thing could be due to anyone. So if you take a conductor like this, and let's say if you bring a plus Q here, we know there are a lot of electrons sitting inside. These electrons are attracted. The free electrons move opposite to the external field because electrons are negative charge. So in this case, the plus Q will attract them. But understand, immediately everything won't come here. Some electrons will come here. Some positive charge will come here, right? And now if you look at these electrons here, there is a, let me use a different color. Some electrons will come here and some positive charge will come here. So if you take an electron here, so this guy is still attracting here. So this is your F external. Now see what happens. If this electron tries to go to the left side, the electrons which are sitting here already, they will repel. And these positive charges here will already attract. So they will create some force, F induced in the opposite direction. You're getting it? So this is an intermediate stage. So the moment you keep something, suddenly you won't get charges. There's a slight delay in nanoseconds. So here if you see, there is a force on the electrons due to the induced charges now. Right, which opposes the external force. But that F external is still stronger than F induced. So more and more and more charges will keep going. At one point, you will reach such a stage. This thing gets induced a lot of charge here, minus Q, and this thing becomes, you reach the steady state. So even in charge distributions, right, there's a steady state, but it just takes a nanosecond, so it gets on pretty fast. So now if you take an electron here, so this F external force is getting balanced by the F induced force. So this, you have reached a steady state. F external becomes equal to F induced. Therefore, net force on the electron is zero. Therefore, if force is zero, the net field is zero. You're getting it? So the final statement here is the field due to induced charges. So when you keep an external field, it will create some induced charges. Cancels out the external field. So if someone asks you this question, is the outside charge still attracting the electrons? Yes. Are the induced charges attracting the electrons? Yes. But is the net force zero? Yes. So the outside force suddenly doesn't become zero there. So this is what we get. The field inside a conductor . due to all static charge distributions is 0. That word is important, huh? Static charge distributions. If the charges are moving outside, the system will never reach equilibrium. So you can directly take this. Doesn't matter. Like you put how much ever charge you want outside the field, inside a conductor is 0. God, we are talking about field inside, not the lines outside. The force due to this charge between these two and the force between this charge and this are cancelling out. Don't get confused between lines and that has nothing to do with each other. Make sense? Everyone is clear with the story, what is happening here. So the argument is always like this. If the field is not 0 inside a conductor, what will happen? The electrons will go opposite to the field. The electrons will keep going, creating more and more induced charge till the induced charge cancels the external field. Think of like this, huh? The situation has become like this. Let's say there is a room here. There is a room here. Okay? And let's say there is a door like this. So there are 50 people here and there are 50 people here. So I come here. What I do, I catch every person in this room B and I throw them into room A. So whoever comes near the door, I'll catch them and throw them into the room. So this will become 51 and 49. So it is still kind of okay. I keep throwing. At one point, this guy will become 60 and this will become 40. Now you tell me, if I try to throw one more person, this place is getting crammed, isn't it? So these people here will try to oppose, isn't it? They said, yeah, don't push any more people here. We don't have space. And here it is getting vacant. So this guy doesn't want to go inside. He wants to be here because it is empty. You're getting it? But still, I'm stronger. So I will still keep pushing people. At one point, I'll reach a number like 75 and 25. Now, can you see what is happening? Now it becomes more difficult to push one more person inside, isn't it? At one point, the resistance will become so much, we reach an equilibrium, let's say 80 and 20. At this point, my force is equal to the repulsion from these guys and the attraction towards these guys, and the charge is stuck. You can't move any more charges. But the moment I go away from here, what will happen? The people will again come back to this room, isn't it? Everything will get stabilized. So basically, the external charge outside is holding these induced charges and keeping there from not mixing up. So some people generally get a doubt like, sir, if there is a minus and plus, why are these not going? That is because this guy is holding these charges and keeping it away from not going to the positive charge. Is this clear, everyone? So now if we just write this down, so this is what you are asking, Sainas, here. So if you have a conductor here, and if this was plus Q, so this was your minus charge. This was your plus charge. This is plus Q and this is minus Q. So if you draw the field line diagrams, this is how it should look. Every field line will enter perpendicular to the surface. Why? Simple reason. Initially, so inside the field is 0. Just now we proved conductor. Therefore, the potential must be constant. E is dV by dr. Therefore, this is equipotential. There will be no field lines inside a conductor. Are you getting this? For an equipotential surface, how is the electric field? It will be always perpendicular. So the field lines will enter perpendicularly and will leave perpendicular from the surface. Now, can someone tell me why can't I have a field line like this? Positive to negative, why can't I have a field line like this? Induction, equipotential, so yeah, right, Saina. So remember the statement, in the direction of the electric field, the potential changes. Do you remember that? Minus integral E dot dr. That means when you go from here to here through this field line, the potential between here and here should be different, isn't it? But you said it is an equipotential surface, so such a line cannot exist. So there are more lines here. So a few points here. First thing, Q is greater than Q. We proved this before. Number of lines of plus Q are more. Second thing, the field lines always enter and leave perpendicular to the surface. Always enter and leave perpendicular to the conductor. Because it is equipotential. Next thing. So when you took this negative and when you took this positive, these lines, this is not possible. You can't have a line like this. Reason, in the direction of field potential changes. But the conductor is equipotential. Clear, everyone? Next thing. So that is one important thing. The field inside a conductor is zero. We proved it. So you can use that statement liberally everywhere. But just be careful. It's a field inside a conductor due to static charge distributions. If you have a charge field outside running around, that will keep on messing up the field inside. You will never reach a steady state. But we can ignore for small velocities. Clear? Going ahead. Next thing. Charge distribution on a conductor. So whenever you give charge to a conductor, how does it distribute? So listen, all these things are theory. You'll get pretty decent questions on this. The only problem with these kind of questions, right? There is no proofs or formulas. You always have to prove it with statements. Because this happens, this is going to happen. Case 1. Charge is given to a conductor. So if you have a conductor and if you give charge Q, so how does this charge distribute? So we have a conductor. Let's say someone gave charge Q. So in this conductor, consider a Gaussian surface. So take a random Gaussian surface. We know since it is a conductor, field is zero. Therefore, flux is zero. This implies charge enclosed is zero. That means if you take a conductor and give a charge, there cannot be any charge inside the conductor. Charge cannot exist in the bulk of the conductor. Charge can exist only on the surfaces. That means whenever you give charge Q to a conductor, you can be sure all the charge will distribute only on the surface. Uniform, non-uniform, that depends. Charge cannot be inside. There is no charge inside anywhere. So that means, remember that uniformly charged sphere we keep talking about, that was actually an insulator. If you take a solid conductor sphere and you put a charge, it will go into the surface. It behaves like a hollow shell. Now, there is a more logical way of proving this also. Think about it. When you're giving positive charge, you're giving like charges, isn't it? What do like charges do? They repel each other. So they will try to go as far as possible, isn't it? What is as far as possible? Surface. Is that making sense? If I take 10 of you and throw in a room and all of you hate each other and trying to kill each other, where will you sit? You will try to sit as far as possible near the walls, isn't it? No one will come and sit in the middle. It is scary. So that would be a more logical way of proving it, why the charge can't be inside. If the charge is inside, plus and plus, they will repel. They will fly off to as far as possible. As far as possible is the surface. You can't go more than that. Is that making sense? That's a more logical way of proving. This thing I proved more with a Gauss law and all, more scientific. Any doubts on this thing? So let's be very clear with these cases which I'm teaching now. Clear? Case 2. You took a conductor with a cavity. And now you gave charge Q. So now my doubt is, will there be any charge inside the cavity? So let's assume there is a small charge here, small q, then the remaining charge should be outside because charge is conserved. Again, same story. Consider a Gaussian surface enclosing the cavity. Now this Gaussian surface you're taking inside a conductor. Field is 0, implies flux is 0, therefore Q is 0. That means if you put a cavity and put charge, the charge will still be on the surface only. The charge won't go inside the cavity. Again, if you see from that logic that I gave you, that analogy, still, if you try to put a positive charge and positive charge, they will repel, right? They would love to go to the surface. Why should they be inside on the inner surface? So if you put a cavity and give a charge, the charge will never enter the cavity. The charge will stay on the surface only. Charge does not enter the cavity. It stays on surface. So that means if you take a conductor, whether you have cavity, no cavity, the charge doesn't care. It will just behave as if on the outer surface. The cavity inside won't be affecting the outside charge here. The charge does not enter the cavity. It remains on surface. Hey, Maglev is completely different concept. Clear? Aditya, Ishan, clear with this? Saina, Rehan, Partika, Udian, clear na? Maulika? No induction on the surface. There is an induction here. You gave this charge Q, na? Charge Q is not outside. You took a charge and dumped it onto the surface. Getting a charge Q is given to the conductor. You're not keeping charge outside. Case 3. What if you take a conductor with a cavity? Let's take some random cavity actually. Let's take a random conductor with a random cavity. Or else you will think it is only valid for spheres. So we have a neutral conductor. And let's say a charge Q is placed inside the cavity. You kept it inside, so there is no gravity, nothing. It is floating. It is not touching the walls, huh? If you touch the walls, you'll go away to the surface. Now, how will this charge distribute? Again, same logic. So this plus Q will be there. Let's say there is some charge here. I don't know how much it is. So let's call it minus Q. Because the outside is neutral, the outside will become plus Q. Think of like this. The plus Q inside is attracting electrons towards the center. So you'll get vacancies on the surface. Make sense? Now, same story. Use the Gaussian surface. Since you're taking the Gaussian surface, the black one inside a conductor, field is 0. Therefore, flux is 0. Therefore, the charge enclosed Q minus Q is 0. Therefore, Q is equal to capital Q. Means if you put a charge inside a cavity, you will always induce equal and opposite charge on the cavity. So the final diagram would be like this. So if you put plus Q here, you will induce minus Q, and on the surface you'll get a plus Q. The outside one is still neutral. Have a look at this. All getting this? That means, let me take an example here. Let's say we take a sphere with a random cavity like this. Let's take even a sphere also, that also a spherical cavity. But let's say you kept the charge little to the side like this. So what will happen is you will induce more negative charge here and less negative charge here. Because it is more closer to the surface, you'll get more charge there. So if you look at the field lines would be like this. They'll be more crammed up here and they'll be less distributed here. But the inside charge is still minus Q. The total charge enclosed is still 0. So the inside charge is still minus Q. The outside, you'll get a uniform charge distribution. Sorry, that is minus capital Q. And outside, you will get a plus Q. So this is how the field lines would look like. They will leave the surface perpendicularly. So if you see in this example, the charge inside the cavity is not exactly in the center. So it will distribute non-uniform distribution. So I took a spherical surfaces are symmetrical surfaces. Charge inside the spherical cavity is not at center. So wherever it is closer, therefore it induces non-uniform charge distribution. The charge is still equal to minus Q, which we proved in the previous one. So So the charge won't be uniform. So field lengths will be pretty weird. Non-uniform distribution, but total charge is still minus capital Q. So we have a non-uniform field inside. And outside, if you observe, the outside charge is uniform distributed. And there's a reason for this. Why the outside field lengths are not distorted. Think about it. Not a single line from inside is coming out. The reason field lines from inside the cavity are not coming out, because there's a conductor in the middle and it's like a shield. Getting it? The field inside a conductor is zero. Not a single field line will pass through the conductor and come out. Every line that is coming from plus Q gets absorbed by this minus Q inside. So field lengths on the inside of the cavity do not come out. Therefore, charges outside do not know there is something happening inside. Tell me, do you remember the theory of field theory? The whole story, how we started? What is field theory? When a charge is placed, it will create an electric field, modifying the surrounding. And when someone comes in that field, they interact, isn't it? But what if your field lengths are only not coming out? Then no one knows outside you exist, isn't it? So the charges outside, right, they do not know that something is inside. Charges outside are not affected by charges inside the cavity. Therefore, charges outside are not affected. That's why you still get a uniform distribution. Affected by the plus Q and induced charges together. I think that's the full word. Plus Q and induced charges. We will talk about that more in detail. Is this statement making sense, everyone? Since not single line is coming out, the outside charge doesn't know what is happening inside. Clear, everyone? So let me take one more example that will make things more clear. Suppose you have a conductor, you have a cavity. So here you kept a charge Q1 and outside you kept a charge Q2. The distance between these two is some d. Now this Q1, what will it do? It will create some induced charges here, which are non-uniform. I don't know how it is, but I know that value is minus Q1. Agreed? Now what I was saying, not a single field line from here comes outside, so that Q2 does not know. Q2 does not know that Q1 exists. You're getting it? Not a single field line is coming. It doesn't know that there's a chance inside. Does not know that, that there's a cavity only in the first place. Forget about Q1. Does not know that there is a cavity inside. So the force on Q2 due to the plus Q1 and the induced charges minus Q1 is 0. Are you getting it? So can I write like this? So that means the force on Q2 is force between Q1 and Q2 plus force between the minus Q1 and Q2 should be 0. But I know from Coulomb's law, the force between two charges is independent of all other charges. Again, be careful here. Listen to this statement carefully. the Q2 is not getting affected because of this Q1 and minus Q1 together. You're getting it? That Q1 and minus Q1 together will not affect with everyone. But if I ask you only between this Q1 and this Q2, there will still be a force between them, isn't it? So that would be K Q1 Q2 by D square. This is the force between the induced charges. Inside and Q2 outside. So this is 0. So we get the force due to the induced charges on inner cavity on Q2 is minus Q1 Q2 by D square. So there you can actually write down this. The Q1 and its induced charge minus Q1 together will not interact with anyone. Individually they'll interact, but if you take them together, they'll behave as if they're just gone. They don't exist. Think about these things, right? Go through them again once more. We will do next class. We will do more problems on this. You'll get even better understanding. And not interact with any charge. Is this making sense, everyone? So if I ask you this question, the charge inside the cavity and the charge outside, are they repelling? Yes or no? Yes, they're repelling. This charge minus Q1 on the inside and this Q2 are attracting. Yes, they're attracting. But if you take this together, Q2 doesn't know who is there inside. The net force is 0. I hope this is making sense. Individually, there is a still interaction between them, but the net force is 0. So this phenomenon is what we call a shielding effect. This is called a shielding effect. In chemistry, you must have learned, isn't it? The electrons in the 1s orbit or 2s orbit. When the electron is jumping from 3 to 1, the electrons in the 2 will block them. So basically, the electrons get repelled. So if this was your nucleus, the electrons, so let's say there's a vacancy in the first shell. And when an electron from the third shell or the second shell is trying to jump, this electron here will repel this, will not let it come. It's like a partial shielding effect, basically. But here, this thing is a complete thing. Clear with this? So there are more variations of this. So on Friday, when we catch up, we will do it in more, like, there are some pretty good problems. I think once we do 3-4 problems, you'll actually get a hang of what is actually happening. So we will continue this on Friday. So after this Friday, we'll be doing shells also. Mostly we should wrap up another 1.5 class में Gauss law. Next week, we'll wrap it up. Okay, so with this, we'll wrap up for this thing. So any doubts in today's class? Anything else you can ask, or else you're free to leave.
Yes, a small doubt in the last thing only.
बोलो ना.
वो जो बाहर Q2 है, is the net force on Q2 equal to 0? No, ना.
नहीं, वो तो induced charges भी आ गए ना यहाँ पे. That I'm not taking. This is
So
only due
because
to
of them, there will
Q1
be
and
some kind
induced
of
charge.
force.
Yeah. Net force 0 नहीं है.
So
We are
on
only
Q1
talking
जो
about
अंदर
that
है,
cavity.
उसमें net force 0 होगा ना?
Which way?
Q1 inside. The inside
Due
charge.
to whom? Due to whom?
So the overall net force on Q1.
नहीं 0 नहीं होगा. ये नॉन यूनिफॉर्म डिस्ट्रीब्यूशन है ना, minus Q1.
उस पे भी 0 नहीं होगा.
नहीं होगा, because देखो ना, if you make a cavity like this and if you put a charge Q1 like this, if you see, this will put more negative here, this will put less negative here, so it will get attracted towards that side. 0 नहीं है वो. Because see, when you take force on Q1, you should take the field due to the induced charges on Q1. Na? You won't take your own field on yourself. You're getting it? No one from outside will interact with Q1 outside. The only guy who attracts inside is his induced charges. Make sense?
Yes, makes sense.
Getting it? Outside का problem क्या होगा? अभी Q2 is there ना? That Q2 will induce its own charges outside. So this Q2 and this induced charges will not interact with inside. Think of like this. in this diagram, if you observe, the field lines from outside are blocked by the surface charges, isn't it? Huh, Ishan?
Yes, sir, Samsha.
That means if you have a cavity here, this cavity doesn't know Q exists outside. So vice versa. If the inside ones can't interact with outside charges can't interact with inside. We will talk about it in more detail next class में करेंगे, but I hope you got the idea there.
But this inside outside thing is in pairs, right? Like
It is always in pairs. Matlab, this Q1 and this minus Q1 together will not interact with anyone. The pairs.
so the
That's-
induced charges from Q2 on the conductor can interact with Q1.
Meaning, let's say a minus Q. You are saying only this charge.
Yeah.
Only that charge will interact. But if you take Q2 and this charge together, they won't interact. No, because see, every field line is coming here and stopping here. Why is the field line stopping here? Because of this induced charge, right? So this Q2 and this plus Q and minus Q, these three together will not interact with anyone inside. Saina?
Right. So the net force on Q1 inside.
We'll
Will
talk
it
about
be-
that in next verse. Next net force we'll talk about next class. We are just talking about pairs only now. Net forces will be different. That won't be zero. Net force is pretty messed up. There'll be too many things. यहाँ पे surface में charge Q1 आएगा, ये Q2 का induced charge आएगा, ये Q2 है. There'll be a lot of things on the surface. So net force will not be zero. ठीक है?
Also, I wanted to ask if I have